Thank you for joining us for my talk. Okay, today we'll discuss green computing with computational storage devices. I'm Changho Choi. I'm a Senior Director of Engineering in Memory Solutions Lab in Samsung in San Jose. My colleague Yangwook Kang, he is a Senior Staff Engineer. He will present today with me. First, I will briefly discuss industry trends, and then we'll discuss computational storage, including what is computational storage, and also we will present one of example of a computational storage that is a Samsung Smart SSD. We also measured some computational storage benefit with Samsung Smart SSD, so we will discuss some performance evaluation system, and also we'll discuss the benefit of the computational storage. Finally, we will wrap up our talk in summary. First, I wanted to start with data center energy consumption. As you see here, this statistics in 2018, but I think this is well measured numbers. On the top, as you see, global electricity demand is almost 20,000 terawatt hours. Out of this one, almost 10% was used for information and communication technology sectors. And data center itself, it consumes almost 1% of global energy demand. 200 terawatt hour is same as energy consumption in one country, Vietnam. So Vietnam is almost the 20th country that uses a high number of energies. So you could get an idea. So data centers energy consumption is more than small countries' full energy consumption. As you see in this graph, energy consumption and energy demand increase as time goes. Based on the research, 2030, almost 9,000 terawatt hours is required for information and communication technology sectors. That is almost 21% of total global energy consumption. Out of this one, data center uses almost 30% of this one. So energy consumption of data center will increase as time goes. This the graph shows the energy consumption inside the data center. As you see here in this figure, almost 43% of data center energy consumed by servers. Inside the server, more than 60% of energy consumed by CPUs. So if you use CPU utilization lower, then I'm pretty sure we could reduce energy consumption in the server and also energy consumption in data center. Energy consumption is one of the big concerns nowadays in data center. And another industry trend is domain-specific architecture. As you see in this diagram, even though number of transistors increases exponentially as time goes, and also the frequency of CPU utilization, so frequency of process is saturated, and the single thread performance is already started saturated, meaning that we cannot increase exponentially for processing power as time goes, as we enjoyed in the past. Even though the process performance is saturating, the amount of data increases as time goes. It grows almost exponentially every year. Because of this one, we cannot process all data generated in the world with current processor and current processing power. That's the reason we thought, people thought data gravity. Instead of moving data, huge data from storage to the processing unit like a CPU, people started thinking moving application and services to the data. That reduced a lot of costs moving big data from storage to the processing units. As the amount of data grows and the amount of data getting bigger, they will attract applications and services to the data more to get the more throughput and lower the latency of data processing. We could achieve some processing, NeoData processing with many different components. We could use a GPU or FPGA on the host and process data. But if you use a GPU and FPGA, each device occupies many PCI slots and lanes. And the limited number of high-speed SSDs it limits the installing of a high number of high-speed SSDs because of lack of PCI slots or PCI lanes. Also, if we use a GPU or FPGA, we need to develop effective control paths and data paths together because we need to move data from storage to the processing unit like a GPU and FPGA. Also, as you already understand, GPU and FPGA, they spend a huge amount of powers. So it requires a lot of powers to process data in GPU and FPGA. Instead of running the process in separate device, there is some benefit if we run some operation inside the storage device. We call it in-storage computing. So with in-storage computing, we could leverage high internal I/O bandwidth, and also the data is processed SSD controller or some accelerator inside the device. Also, we could accommodate internal hardware resources and performance based on the user requirement and use cases. For example, we could use ARM cores if some processing does not require high processing capability. Or we could use ASIC, or we could use FPGA, depends on the application and use cases or data types. Also, we could adjust the computing unit DRAM usage based on data types and data sizes, and also the computational capability. So we could customize internal hardware resources based on use cases and data set. If we run the processing inside the storage device, we don't need to use extra PCI slot or PCI lanes, even though we could process high-speed accelerated data processing inside the device. This way, we could achieve a high scalability of performance. We'll show how we could get performance scales when we discuss technical details and our performance evaluation. Based on this industry, we need to develop a data domain specific architecture. Computational storage is one of a big component of data domain specific architecture. SNIA standard group, industry standard group, they defined computational storage as computational storage drives, computational storage array, and computational storage processor. What is a computational storage drive? Computational storage drive is composed of persistent data storage like NAND flash and computation modules. In the SNIA spec and also NVMe standard group, we call it computational engines. Samsung Smart SSD is one of the leading computational storage drive. As you already imagine, inside the Samsung Smart SSD, we have a NAND flash. In addition to that, we have hardware acceleration engines. Current Samsung Smart SSD embedded FPGA inside the device, and then we run some acceleration in FPGA device. As I said, industry moves fast for computational storage initiatives. NVMe storage, the standard group, they are actively working on NVMe computational storage initiative, including TP4091 and TP4131. TP4091 is mostly for computational programs and command set specification. And TP4131 is mainly handle memory management for computational storage. Inside the SNIA, two main activities is ongoing. The first one is that they are defining computational storage architecture and programming model. They released version 1.0 for computational storage architecture and programming model for public review. So you could download and you could review the spec from the SNIA website. And second thing is the computational storage API. They defined the computational storage API that can be leveraged by application. Once application is developed on top of computational storage API, the application is not necessarily to be changed in the future, even though underlying computational storage interface changes. SNIA also released the computational storage API standard spec in SNIA website. You could go to their site and you could download also. As I briefly mentioned that Samsung is a leader of computational storage device developers. Also, we actively participated in computational storage standard work in both NVMe and SNIA standard group. As I briefly mentioned that Samsung Smart SSD is composed of a storage component, that is a NAND flash component. In addition to that, we have hardware acceleration engines that is accelerating FPGA inside the device. Inside the device, we developed a hardware IP that as a storage engine, a computational storage engine. Some operations like a DB scan and filter operations. This is at-rest data processing, so it would be more secure instead of transferring data from SSD to the host. That is one of the big concerns and big interest from data center and hyperscaler the industry. Samsung developed already 2 generation Smart SSD. First generation Smart SSD was released and it is publicly available. And this one has 2 components inside the device. And this is a Smart SS 1.0. In the Smart SS 1.0, there is a PCI switch inside the device. Through host could access storage through the NVMe command. That is a normal NVMe command for storage I/O, like a read and write. And also host could access accelerator. This is FPGA. But the host needed to access accelerator through the Xilinx whole software stack. So one device is exposed to two devices, one as a NVMe device, the other one is one FPGA device. So user could run some acceleration, and user could transfer data from SSD to accelerator without going through any host memory. This happens through the P2P inside the device. If we move to second generation Smart SSD, second generation Smart SSD has a FPGA component also. In addition to that, we have ARM cores inside the device. This whole component is accessed through the NVMe command itself. So no more FPGA software infrastructure is required to run acceleration inside the Smart SSD in second generation Smart SSD. Also, data transfers happens from inside the device from NAND flash to memory, FPGA memory, and FPGA access data in FPGA memory and run the acceleration. This second generation Smart SSD, as I said, both the components is accessed through the NVMe command set. This one is developed working draft of NVMe spec that is defined by NVMe technical work group. That is TP4091. So at least for now, even though the standard spec has not been finalized, we developed all command set based on the working draft of NVMe command set. Okay. My colleague Yangwook will discuss our performance evaluation and our host stack to enable hardware acceleration inside the device, and he will discuss benefit also.
Hello. So, to demonstrate the processing capability and energy efficiency of the second generation Smart SSDs, we picked a database scan, sequential scan operation as an example. Sequential scan is considered as one of the slowest scan methods in database systems because each row of the table needs to be read and checked for the validity of a condition. It's possible to optimize its performance, but it typically requires many threads to have an increased degree of parallelism, incurring high CPU and memory overheads. So we found that this process is interesting because it has both high demands of I/O and computation, and also a high chance of data reduction. So, so we thought we can be a good target application for our FPGA-based CSD. And then we chose Postgres as our target device because a target database because it is a popular database system widely deployed to data warehouses, and also it provides a flexible plugin module where we can reprogram its sequential scan processing logic. This shows the overall architecture of our system. There are four main software components in the host side. The custom scan plugin, which parses a user query, and the scan solver, which processes the scan commands and then schedules the I/O commands. And SNIA CS API provides an access to Smart SSD through a standard API. And finally, the NVMe device driver that implements the TP4091, the Computational Storage standard proposal. So on the device side, Smart SSD has the storage controller, like for NAND, like other normal NVMe SSDs. And it additionally has a compute engine, which is running on the embedded ARM processor. This ARM processor runs the user program written in eBPF, which is the programming language originally designed to run inside the OS kernel. But it provides additional security, so the TP4091 standard is requiring eBPF as a format of the user program. And we added a few more built-in functions so that the eBPF programs can access FPGA or ASIC inside the device. So when a query is given from a user, first the custom scan will check and see if the query can be processed accelerated by our hardware. Then it parses the query and generates a scan request for the scan solver. Then the scan solver fetches that command and then also retrieves the physical location of DB pages from a file system and start prefetching data into device DRAM. In the meantime, Smart SSD FPGA is also configured for a given query. So when both processes are ready, then scan server starts sending the scan commands to Smart SSDs, and then inside the device, the scan eBPF program will receive the command, wait for its completion, and then do any post-processing if required. After scan is processed, then scan server will fetch the result from the in-device DRAM to host DRAM, and then the result will be shared with the custom scan via IPC. Then custom scan will finally parses the scan output and then pass that to the Postgres. So this data prefetching and scan and result retrieving tasks are running in parallel, processing data until the entire table is scanned. So we just discussed the software modules here, and all the software modules are written by Samsung, and they will be fully open sourced later. We expect early next year. And thanks to Postgres' plugin architecture, we didn't have to change the existing Postgres code. We just modify one line of PostgreSQL's configuration file to enable the new feature. And then this figure illustrates where the processing happens and how much data is transferred between the host system and then device in two systems to show where the benefit comes from in our Postgres with Smart SSD configuration. So when we use a Postgres on CPU, typically, for the scan operation, they need to load the entire raw data to the host DRAM, and then the scan thread will process each tuple in the database page and then produce the scan result. And then the scan result will be fetched by other components in the database system for further processing, such as sorting or aggregations and join other operations. In the Postgres with Smart SSD case, the raw data is not transferred to the host system. The SSDs internally reads the DB pages into device DRAM, and then it processes and then notify the host system. The host system will just send a scan request to the device, and the scan will be performed by the FPGA, eBPF and FPGA module we programmed. And then the final result, only the final result will be fetched back to the host DRAM, so saving the disk bandwidth. So in the Postgres with CPU case, to optimize performance, we need to increase the number of threads. And in the Postgres with Smart SSD case, we are still using multiple threads, but most of the time, all the threads are in the slim mode after sending the request to the device. So we have a very low CPU utilization. We can achieve very low CPU utilization with this approach. So the right side, we have a summary. Because we don't have to send raw data, we can only transfer a small amount of data. And another benefit is we are not using host CPU to handle the I/O. So the actual loading of data and then putting it to the DRAM part is controlled by the SSD controller in the device. So it's kind of free operation for the CPU's perspective. And so that's why we can get the very low host system resource usage. And the FPGA and all these smart SSDs are consuming much less power than host CPUs. So we can do more like energy efficient processing inside the device. And then it can, because it's an independent computing unit, so you can add more devices to get more performance. So what I just discussed so far is the software architecture for our scan acceleration engine. Now let me discuss the design of our hardware acceleration engine. So our hardware acceleration engine consists of multiple independent scan kernels. Then each scan kernel can process different query. This means multiple concurrent queries can be assigned to each kernel, or large data for one query can be split into multiple kernels and executed at the same time. And each kernel processes DB pages using stream processing manner rather than batch processing manner. This allows that the computing on the column data can happen as soon as the data is fetched from the DB page, extracted from a DB page. So we wanted to have a very high parallelism and a high utilization of hardware components during the whole scan processing this way. And then also in each kernel, we have multiple filter logics. So they can execute all the where clause conditions at the same time. So we can achieve parallelism per query processing too. So by doing so, the scan engine can execute multiple queries, multiple filter conditions in parallel, stream processing each row is in a database pages. So performance-wise, our scan engine, hardware engine, is performing at line speed, which means it's a little bit faster than actual I/O throughput in the device, so we can effectively hide the scan latency from users. So let me go over the evaluation configuration we have. We evaluate our system using 8 smart SSDs and Postgres 13 with 1 terabyte TPCH dataset. And then we use the TPCH Core 6 for scalability and performance evaluation, because this is a select query scanning the largest table in the TPCH dataset. So this shows our result. The blue bar represents the performance or the energy consumption of the Postgres running on CPU, and green bar represents the performance of our second generation Smart SSD. So when you look at the energy usage chart, it shows that the Postgres with Smart SSD uses 2 to 7 times less energy than the host system. This is because amount of data movement is reduced, and then also CPU utilizations on the host side is reduced, and more energy efficient processing in the device was possible through offloading. When you look at the right side, the CPU utilization chart, you can see that the host system is suffering from CPU bottleneck as we increase the number of devices in the system. So after 4 devices, average will go above 75%, and sometimes hitting 100%, and does not providing more performance after that. On the other hand, our device CPU utilization is very low. It remained very low because most of the host side thread is just sleeping, and we found that with 8 devices, we are using less than 5 CPU cores, which is less than the 1 CPU core per devices, while saturating the entire bandwidth of the device. So when you look at the end-to-end throughput chart in the middle, you can see that the green bar linearly increases as the number of devices increases, while the blue bar is stop increasing after 4 devices. So overall, we have been noticing that the more and more CPU resources are required to saturate modern flash devices as PCI bandwidth increases. We believe that in storage offloading will be one of the key features of the future storage and data processing engines because it can achieve both high performance and energy efficiency at the same time. So we discussed the benefit of scan offloading with Smart SSD in terms of energy efficiency, throughput, and CPU utilization. And our evaluation shows that with 8 devices, we can achieve 7 times better energy efficiency, 7 times better throughput, and 11 times lower CPU utilization. And also, I'd like to mention that while not discussed in detail in this slide, we also believe that avoiding fetching the entire raw data to the host system can help improve the security of the system because the attackers will not see the entire contents. They can only see the processed result, the partial data, when they are doing the network sniffing or memory sniffing. So
Thank you, Yangwook. Okay, so I want to conclude our talk with call for action. As you may already know, Samsung have a small booth outside. I recommend you to visit the Samsung booth and get more information. And also we have other sessions on computational storage that is presented by colleagues in Samsung. So if some of them is already presented, so I recommend you to go to our site and see their presentation, including keynotes from VPK in Memory Solutions Lab. And finally, I wanted to invite you guys to join standard activities in SNIA and NVMe for computational storage. Thank you for your attention.